Right?
Hello everyone, we are Ruben and Nirupa, and today we will present our project to separate facial tissue editing using diffusion model. Diffusion model dan stable diffusion can generate negative image for people. However, separate image editing skill when set up is having the original structure and identity to the next graph consistency and maintain semantic alignment with take from the main objective of the object research to compare to fine-tuning schedule for stable diffusion, full fine-tuning and non-random organization to evaluate their changes of in terms of memory, quality, review, memory, sending time, and deployment efficiency. Dataset execution where user instruct to bit dataset with provided cheapness, original image, instruction, edited image, for example, from nine image look nine picture, transform the image accordingly, the dataset is translated. Fine-tuning stable diffusion with NORA and quantization NORA of all now-run adapted to user number of changeable parameter views still acting the model effectively. Quantization also author can convert research model way to now precision with memory of speed capturing. By combining NORA and quantization, we can achieve efficient fine-tuning of stable diffusion with minimal loss in quality. By combining NORA and quantization, we can achieve efficient fine-tuning of stable diffusion with minimal loss in quality. Connected encoder. The connected text encoder converts text form into everything pattern that the model can understand. The everything are passed into the unit interface and technology to generate the target image. This what create helps the model understand the meaning behind the text and translate it into visual children. Not person and optimizer. The not person is for the efficient between the generated image and target image on optimizer and update the model way to minimize it not together. The A is for the model value in learning the correct way to modify image based on attribute.
So in this project, we use to the DDMP, which is a scatter line in the Latin space. In this process, the images will gradually be added by the noise. That make model will train to predict the noise in the reverse process, as like the right slide. So at the same time, we also set up the fine-tuning configuration with the three learning Z from 1L -5 to the 5r minus 5. So it determines the step size after each iteration while moving towards. We also set up the approach to the fitted, and the resolution of image is 256. That can improve the quality, but also similar to increasing the computation. Uh, with the optimizer is alarm, and I also set to the 8, and in right side I used to know that with it that it been control the size of the nose magic, as magic A and B. That output is 8 material 8, and round 5 is 60 with iterating with configuration time is from ET 16 to the ET8. That can reduce the model weight during the training. So this is the result of normal fine-tuning. When in the image target appeared, it just changed the color of the color of prompt, but in the target but in the generation that my model predicted, its appearance can change the context. I mean that despite the fine-tuning is very comprehensive, and it also more effective than the image target during the training during the model original model training. So look at this one. This is the performance of each learning rate that I used to test in this report. When the learning rate, when I see the learning rate 5 R minus 5 can achieve more high performance than the other than both of the learning rate. Despite it's not maintain the contact, but you also change the spec to the user demand or user prompt. So this is a result of design grid configuration, because when look at this one, this approach can achieve the expected output, where it can generate the image that can change with this spec to the user prompt. Despite it also take a lot, or it also return many nodes of the feature, but it can change but it can change this spec to the user demand. So I also evaluated this read model, this spec to 3 band magic, which is PA prompt adherence, and SI is the structural integrity, and final is TSF is the target style fidelity. When look at this one, the nosing, rotten, and quantization can remain competitive and efficient after printed the images. And I also test with 5 prompt. That is the previous slide I showed. And during the training and convergence, when in the image, both image above, that is the normal training. When the model can can reduce gradually, and it also so the performance is very good. It can read the 0.09 to the 0 and 0.7. In the training time for each step, when in the first 10 approach, the model can take many time to training, but after that, it can just take take a 4 seconds. That can gradually remain the load function blockchain. And when I chain with the quantization and when and know that I also achieve the need to beat the CPU than the normal chaining, normal fine tuning. And the time step you also reduce many time that can reduce the performance, but you also achieve the high expected value, where step not just achieve the 0.1 respect to the 0.07 with the normal fine tuning, and the CPU a lot can take a few HD away. So in conclusion, the quantitative model can more 1.45 step, and that's so fast and efficient. So that's all my presentation. Thank you.